Hello friends, welcome to lecture 8.5 on the in the unit on discrete wavelet transforms. Until now we have looked at the theoretical aspects of DWT, we have studied extensively the orthogonal DWT and the properties of wavelets, how to compute the DWT. When we say DWT, by default it is understood as orthogonal DWT. So, how to decompose the signals into different scales or different frequency bands and how to reconstruct or synthesize, and studied certain key relations between the properties of the wavelet such as compact support and vanishing moments and so on. In this lecture what we are going to do is look at the practical aspects, both how to implement in the sense how to compute the DWT in MATLAB, and study briefly on the boundary effects. Remember, DWT involves convolution like CWT and any convolution operation is affected by the border effects, that is how the signal behaves at the borders, that is outside the observation interval. And we are going to primarily discuss three popular applications of DWT, namely the discontinuity detection and more popular ones such as signal compression and signal estimation. Again, I will show you how to do things in MATLAB with a few illustrative examples. So, let us begin our journey. The first thing that we would like to do in MATLAB is to be able to understand, to be able to generate wavelets, which we have seen of course yesterday, but get the different wavelets or different filter coefficients and so on. I have already discussed that routine with you. We are going to primarily use the MATLAB's Wavelet Toolbox, and the routine that gets the wavelets or for you or wavelet filters are WaveFun and W filters. We have seen the usage of WaveFun earlier. So, suppose I want to generate a Haar wavelet, then again I use the WaveFun and I want to have the scaling function, the wavelet and the values at which these are being computed. In the Haar case, remember that we have an explicit expression, we do not have to compute the scaling function or the wavelets from the filter coefficients. We know already that the scaling function is a box function and the wavelet function is a box with a reversal of the sign halfway through, right. So, the second argument here, as we have seen earlier, represents the number of iterations it takes to compute the wavelets from the filters. For the Haar wavelet alone and a few other wavelets for which closed form expressions exist, this second argument is simply going to tell the WaveFun as to how many points at which the scaling function or the wavelet have to be generated. So, here if I look at the length of phi Haar, it is roughly 2 power 8 plus 2, right. I mean it does not give, normally for wavelets which have closed form expressions, the second argument in WaveFun will generate the scaling function or the wavelet at 2 power that second argument. But here the additional thing that is done is 2 power 8 plus the length of the filter. Okay. So, let us plot the scaling function for the Haar wavelet, and it is a familiar figure for us. So, this is how it looks like, it is a box function, and we can also plot on the same figure the wavelet as well, because the scaling functions and the wavelets are returned as row vectors, we should force them as column vectors, and therefore, you can see now the scaling function and the wavelet are scaling function is shown in blue and the wavelet is shown in red. We can actually ask for a thicker line width to improve the visibility. So, now hopefully you are able to see the scaling function and the wavelet. Very often one has difficulty in visualizing how these functions, whether phi of t or psi of t, look like when they are scaled and translated, either dilated or compressed. Normally we are interested in the dilated versions, because as we have learnt earlier, the signal is available at the finest time resolution, and we always end up constructing only approximations, and approximations are generated by the dilated version. So, assume that this scaling function or the wavelet that we have plot is available here at the same resolution as the signal, and we want to generate phi of t by 2 or even phi of t by 2 minus 1. Then let us first understand by hand how to generate these values. If I am given the phi of t, which here we know is the box function in the interval 0 to 1, which means it is understood to be 0 outside this interval, then I would like to construct phi of t by 2. It is fairly easy. The first step is to have a dummy variable which is equal to t by 2. So, let us call this dummy variable as t prime, and now all I have to do is evaluate phi of t prime given this information. Note that this t is a dummy variable. It tells me essentially what is the value of phi at any value that t takes here. So, that is how you interpret the information. So, let us understand how to do this. So, I would like to evaluate phi of t by 2. Let us call that as phi of t prime, and my objective is to calculate what is phi of t prime as a function of t given this information. So, what we shall do is we shall take values of t here, but instead track phi of t prime, right, because eventually I want to plot phi of t by 2 versus t, that goal does not go away. So, when t is 0, of course, t prime is 0. So, what we shall do is we shall have another row for t prime, and then a third row for phi of t prime, which is nothing but my phi of t by 2. So, when t is 0, t prime is 0, and let us pick another value here. When t is, let us say, half, then t prime is 1/4. So, I know phi of, by the way, phi of t prime, therefore, when I am evaluating phi of t prime at t prime equals 0, I am asking what is phi at 0. Phi at 0 by definition is 1, and likewise here phi at 1/4 is 1, because at any value in this interval 0 to 1, phi assumes a value of 1, right. So, I have here, and then I pick 1 here for t, therefore, I get half, likewise I get phi of t prime to be 1, and so on. So, if I pick here 1.5, I have 0.75 for t prime, once again the value is 1, and when t is 2, t prime is 1, right, and then I have phi to be 1 at this point. As you can see, already phi of t prime is a dilated version. Why? Because phi of t is 1 in the interval 0 to 1, but phi of t by 2 is 1 in the interval 0 to 2. So, it has been already stretched. The moment I step out of this interval 2.5, let us say 1.25, it goes to 0, and so on. So, even if I look at 3, therefore, it remains 0. So, if I were to draw phi of t prime, this is how it would look like. This is how phi of t looks like, and let us say this is 1 and here is 1. So, this is how phi of t looks like. Here the x axis is t, y axis is phi of t. Now, I am going to draw phi of t prime or phi of t by 2. So, the x axis is still t, right, x axis is still t, but y axis is phi of t by 2 and I have 0, 1 and then here 2. This table here tells me that phi of t by 2 is now a dilated version and goes to 0 after this. You see that? Now, I need to compute, remember not only do I need to compute phi of t by 2, I need to be able to compute integer translates of this. At any scale, the approximation coefficients in theory are the inner products of the signal with the scaling function at that scale and its translates. So, how does phi of t by 2 minus 1 look like? Obviously, we do not use this to compute the coefficients, we use the fast algorithm, but you should be really comfortable in visualizing what how phi of t by 2 looks like and how its integer translates look like. So, let us ask what is phi of t by 2 minus 1, the first translate, all right. So, now let us call this as t prime. So, what we are going to do is we are going to erase this values here and ask how phi of t prime, now my t prime is no longer t by 2, but it is t by 2 minus 1, right. So, when t is 0, what is t prime? T prime is minus 1, correct. So, what is phi at minus 1? This information is the key. Phi at minus 1 by definition here is 0 for the Haar scaling function. So, 0. When t is half, I have 1/4 minus 1. So, I have minus 0.75 and once again this is 0. When t is 1, I have minus t prime is minus 0.5. So, phi of t prime remains 0 and when t is 1.5, t prime is minus 0.25 and phi remains 0. When t is 2, then t prime is 1 and that t prime is 0 and that is when the phi of t prime switches on, right. And when t is 2.5, I have here 0.25 and phi remains 1 and so on. So, the last value here at which it remains 1 is t equals 4, at which point t prime is 1 and beyond 4 t prime is greater than 1, as a result phi of t prime is 0. Okay. So, how does the plot of phi of t by 2 minus 1 look like? Just for convenience sake, we shall draw here on the same plot. Now, we will use a different color to plot phi of t by 2 minus 1. It says that this table tells me that phi of t by 2 minus 1 remains 0 until t takes on a value of 2, right. So, it is going to remain 0 here and really what is going to happen is at this point phi of t by 2 minus 1 takes a value of 1 and remains non-zero until 4, remains 1 until t takes a value of 4 and then it goes to 0 once again. So, now it is very clear that at any scale the integer translates of the scaling function are non overlapping. In fact, if you take the inner product of these two, it will turn out to be 0, right. And you can repeat this exercise for yourself for the wavelet as well. The only difference is the wavelet has this shape as you can see on the board. Okay, so, this is blue, we have the scaling function and the wavelet looks like this. Right. In fact, they are different. Let me actually, the values are different as you can see. Yeah, so it actually goes this way, right. Okay. So, that is how the wavelet looks like. Once again you can write a table for psi of t by 2 and psi of all its integer translates and get an idea. Once you have done this for 1 or 2 integer translates, you get an idea of how they look like. But the key point is that we can see the dilation clearly. In fact, phi of t by 4 would extend until 4 and so on. All right. So, this is a useful exercise to understand how these wavelets or scaling functions and the dilations and translations look like. And now get back, and of course, you can use this wave fun to generate a number of wavelets, and if you want to know what wavelets are available, type wave info at the command prompt and it will give you all the different classes of wavelets that have been coded in this toolbox. Namely there is something called crude wavelets. Actually, there is nothing crude about this. They are essentially the complex or the real valued wavelets which do not have necessarily an admissibility constant, or they do not have a scaling function in the sense of DWT. So, the family of wavelets that fall into this category are the Morlet wavelets, the Mexican hat. Actually, Mexican hat wavelet has a scaling function. So, in some sense this is misleading. It tells you that there is no scaling function, but there is a scaling function that is useful in CWT, but not useful in DWT. The scaling function that comes out of a Mexican hat does not have the orthonormal property, that is the scaling function and its integer translates do not have the orthonormal property that are necessary for DWT. And that is why it is said here that there is no scaling function, but that is not entirely true. And then you have infinitely regular wavelets. What this means is that there are a number of the vanishing moments are very high, and the properties of each of this family is given here. So, if you look at the Mayer wavelets, these are the only regular wavelets which do not have a compact support necessarily. In fact, they do not have a compact support, but the scaling function that comes out of the Mayer wavelet can be used for DWT. So, if you look at the properties here, phi exists and the analysis is orthogonal, which means that the scaling function can be used for DWT, and the psi and phi are indefinitely derivable, which means differentiable. You should understand that. It says that the psi and phi are not compactly supported. In fact, you can ask for the Mayer function and understand why they do not have compact support. We have seen the Mayer wavelet before, but just for our own confirmation, let us actually ask for the Mayer wavelet. Unfortunately, the string that you are supposed to pass on to wavefun is not consistent with the name of the wavelet. So, the correct string that has to be, that is acceptable, is MEYR for whatever reason. So, let us plot the Mayer wavelet. So, this is how the scaling function, the one that is shown in blue is the scaling function, the one that is shown in the red is the wavelet function, both belonging to the Mayer family. It is clear now why the scaling functions or the wavelet functions from the Mayer family do not have a compact support, because they only die down exponentially. Consequently, the filter coefficients associated with this are not going to be of finite length. That means, they are not FIR filters. All right. Now, what does it mean? Well, it means that in DWT you may not get all the nice computational efficiency and so on, and that the phi of t of course has a large number of vanishing moments and so on. So, if you go back to the properties of wavelets, here it says for Mayer wavelets, the filters, the discrete transform exists, but you have to use non-FIR filters. However, they are symmetric, as you have seen from the scaling function. You can see here that the scaling function is symmetric, unlike the Dobeschi wavelet or unlike the Dobeschi scaling function. Then come the family of the orthogonal and compactly supported wavelets. So, you see, as I said in the previous lecture, until Debussy came up with her result, it was somehow believed that there exists no compactly supported wavelet that could be orthogonal except for the Haar wavelet, but that is discontinuous. So, people were in need of an orthogonal compactly supported continuous wavelet, and that was the great contribution by Debussy in showing that one can design such a wavelet. And in this family, once the Debussy wavelet was discovered and designed, the simlets and coiflets that we discussed in the previous lecture also came up, and we have already studied the properties of these wavelets and likewise. So, go through each of this family and you will get the information. Now, let us get to business here and look at how DWT is computed using one of these wavelets. So, for this what we shall do is, we shall take the signal that we had used in one of our lectures, lecture 8.3, where I showed you the DWT of a piecewise regular polynomial from Mallet's book, and let us generate 256 observations of this signal, and let us make sure that this is the signal indeed that we want to analyze. So, this is how it is, so it looks right. Now, I would like to perform DWT of this. Of course, we can do a CWT if you want to detect discontinuities and so on. So, suppose I want to perform a DWT and maybe I want to perform signal compression, let us say, right, I want to compress this. I can perform a 1 level DWT or a 2 level DWT and so on. The basic command here that performs a 1 level DWT is the DWT command itself. It performs only a single level discrete wavelet transform. So, if you have a signal and you want to perform a 1 level DWT, or if you have approximation and detail coefficients at 1 level and you want to go to the next level and so on, this DWT routine is useful. So, let me just show you the usage of this routine. What we shall do is we shall say CA, CD. Essentially, CA, CD are my approximation and detail coefficients of a 1 level DWT that I am going to perform on this signal. And let us use a Haar wavelet. I can use a Debussy and so on. We will do that a bit later. So, now I have the approximation coefficients, detail coefficients from the Haar wavelet decomposition, 1 level Haar wavelet decomposition. It is always convenient to plot the signal and the coefficients. So, in this case I have signal and I have 2 sets of coefficients because I performed 1 level DWT. Therefore, I will plot the signal here and okay. So, we have plotted the signal and next comes the approximation coefficients. In this case, it is always useful to plot the approximation coefficients as a stem plot. Typically, stem plot is the best way to plot, and also make sure that you keep the time index intact. If you just ask for a stem plot, the stem plot would plot approximation coefficients versus their index. But what we want to show here is that the resolution of the approximation coefficients in time has fallen down by a factor of 2. So, what we shall do is let us say n is the length of the signal, and then we shall plot 0 to 2 to n minus 1, or you can say 1 to n, whichever way you want it to be. So, let us take it from 1 to n for convenience and plot CA, and let us plot them in red. So, this is how, and then we shall ask for an axis type. So, this is how the approximation coefficients look like. I will show you the plot in maximum mode, maximized mode once I finish plotting the detailed coefficients. Oops, sorry. Yeah. So, now stem CD, let us plot it in green, and the rest of the story is the same. Oh, okay, axis tight, and then let us maximize this. So, what do I have here? I have the signal on the top, and then I have the approximation coefficients here and the detailed coefficients. So, something interesting emerges here. This is a one level decomposition indeed. Now, if you look at the signal, there are discontinuity locations at these points here. So, let us pick one discontinuity location here. I have a discontinuity location around this point, and correspondingly in the detail coefficients I see a spike, right, and that is true for other discontinuities as well. Of course, you should notice, the first thing that you should notice is that the resolution of the approximation coefficients in time has fallen down by a factor of 2. I have plotted the signal as a continuous plot. Ideally, I should have plotted the signal also as a stem plot, is a discrete signal. But anyway, we know the time sampling interval for the signal. So, here I have sampling interval fallen by a factor multiplied by a factor of 2. So, coming back to the point, wherever there are these sharp changes in the signal, particularly of these types, I notice that there are spikes. It is not that I will have spike in these detailed coefficients at all points of changes, and that is the most important thing. In CWT also we have seen this. We have said that the sharp discontinuities or the singularity points will have a specific signature. What is that signature? That you will see a spike in all the frequency bands. So, if I look at the detailed coefficients here, they are in the frequency band omega max over 2 to omega max. Omega max is a Nyquist frequency of the signal, and approximation is corresponding to the low frequency band 0 to omega max by 2. So, not all sharp changes here belong to the high frequency band. In fact, to be able to say that a point in the signal is a singularity or not, the spikes for those points should occur across many frequency bands. Here we have performed only one level decomposition, but if I perform let us say 3 level decomposition, then I will be able to see those spikes coming in. So, DWT has a different signature here as compared to CWT for some singularities. Now, suppose I want to perform a 3 level decomposition, how do I do it?